Great pleasure this morning to introduce my colleague from Oxford, Professor Alison Etheridge, whose title is The Pain in the Torus, Modelling Populations in the Spatial Continuum. And Alison has promised to say a very few words at the beginning about her life, background, whatever, so I won't introduce her any further, but many thanks, Alison.
Thank you, Frances. Yeah, when Helen emailed me, she said, could I say a few words about career-life balance? And I thought, oh, that's innocuous enough. Yeah, of course I can. Actually, on reflection, I hope that no one was expecting anything terribly deep, because I realised that my own career-life balance rests on a huge amount of good fortune. My husband, because both for many reasons, he's a good cook and various other things, but his parents are both academics. And I think at least in part because he heard firsthand the abominable treatment meted out to his mother as she tried to make a career as a chemist in the 1950s, 60s and 70s. He's always been extremely sensitive to the need to balance my career as well as his own. I should turn the microphone. So, I first met my husband in 1995. Right, can you turn it off again? Can I keep going? Yeah, I don't think you need to stream this. So I first met Lionel in 1985 when I was beginning as a graduate student and he was beginning as a postdoc. And although I think I decided right away this was the guy I was going to marry, whether he had views on it, I don't know, we didn't actually get married for a further 12 years. And the main reason for this was that in those first 10 years after we met, every academic opportunity that came my way, I grabbed with both hands. And so at the end of 10 years, we'd very definitely solved the two-career problem. But our carbon footprint was appalling. I'd worked in Cambridge, Canada, Berkeley, Edinburgh, you name it, I'd been there. And he'd been in Oxford all this time. And I think I realized after 10 years, I was never going to be a great mathematician, right? Nobody's going to remember me for my mathematics. But on the other hand, I would regret it if I didn't have a family. And so I decided the time had come to compromise, and I moved first to London, and then a year later up to Oxford. Now, for most people, moving to Oxford doesn't sound like much of a compromise. But at the time, it was a cut in status, it was a cut in salary, and it was moving to a university which didn't really hold very much academic interest for me. But another example of my extraordinary good fortune is that over the next 10 years, Oxford developed extremely powerful research groups in two areas that I do care about, probability theory and population genetics. And so now I guess if I were to choose a university to work in, very likely it would be Oxford. So that was just good luck. Well, the purpose of moving to Oxford was to have a family. Fortunately, again, another bit of good fortune, I got an EPSRC Advanced Fellowship, so a 5-year research fellowship, a couple of years after moving to Oxford, and that made my schedule very flexible, which made having a family seem all the more realistic. And here's some photographic evidence that we did achieve it. Sorry, the photo's not turned out terribly well. And that's my family in its natural environment, an expensive restaurant somewhere. And so how do we cope? The kids are, how old are they? That one was 6 last week, and my daughter will be 9 in the summer. And the way that we manage is basically, we throw a lot of money at the problem. So they've both been in full-time childcare since they were 3 months old. And these days I drop the kids at school at 10 to 9 in the morning. I go straight to the office. They stay in after school club, and then they're collected by an au pair, taken home. And I get home about 7:15. So from 9 till 7, I'm in the office, working. And I find that as long as I'm extremely disciplined, that's almost enough time. And evenings and weekends is their time. So a bit of email, bit of marking, but no serious work, not the sort of work we used to do. And it pretty much works, but the one thing that really worried me was that I'm not sufficiently self-disciplined to really survive with just 9 till 7. And so I decided that I should change the way that I structure my research. I thought the best thing was to make sure that I couldn't give up research, because that's the thing I really want. At the end of the day, when these guys don't need me anymore and they've left home, I want a research career, because that's the thing that made me become a mathematician. And so, whereas before I had children, almost all my work was single author, since I had children, I did something which might sound a bit counterintuitive. I took on more graduate students, more postdocs, and I invite a lot of visitors to come and visit me in Oxford. Notice to come and visit me in Oxford, so I don't have to travel, because travelling is time being used up. And almost all my work since they were born has been joint author papers. And another stroke of good fortune is I really, really enjoy collaborative research. It is just a lot of fun. And I've had some extremely good collaborators. And one of them is this guy, Nick Barton, who is an evolutionary geneticist in IST Vienna, but because of his own particular career-life balance, he's also one third time in Edinburgh, where his family live. So Nick is also very understanding of the need to develop strategies for coping with having a family. So what I want to talk about is part of what's become a huge and rather amorphous collaboration with Nick, but which is always somehow deep down focused on modelling populations in a spatial continuum. So I thought it would make sense, since he's a theoretical population geneticist, to tell you what one of those is. So the aim of theoretical population genetics is to understand complex patterns of genetic variation that we see in the world around us. And it can find the whole subject can find its origins in what's called the modern evolutionary synthesis. The modern evolutionary synthesis was the process whereby the theories of, on the one hand, Darwin, and on the other hand, Mendel, were reconciled into a single theory. So in case you haven't read The Origin of the Species recently, there's a précis. So Darwin tells us that heritable traits, so traits that are passed on from parent to offspring, that increased reproductive success will become more common in a population. Very simple but important idea. In order for it to work, it requires two things. It requires that the population have variation. If everyone were the same, it wouldn't work. And it requires that offspring be similar to their parents. And the mechanism whereby that works is provided by Mendel. So Mendel tells us that traits are determined by genes, or at least influenced by genes. Genes occur in different types, which we're going to call alleles. It's a technical term, and that gives us that variability in the population. And offspring inherit their genes from their parents, and that gives us the heritability of traits that we need for natural selection to work. So why? It doesn't seem terribly difficult to reconcile these theories, right? Why was reconciliation necessary? Well, Darwin concentrated in all his examples on the way that natural selection could act on very small differences in traits to build up complex adaptations. Whereas Mendel really concentrated on big differences, peas with smooth skins versus wrinkled skins. And these were very, very different ideas. And although these pieces of work were published in the 1850s and 60s, within 7 years of each other, it was a further 50 years before anyone saw how to fit the two theories together. And the people who saw how to fit it together were really three guys: Fisher, Haldane, and Wright. And I've put the role of mathematics here because mathematics was crucial in the work of all of these people. So Fisher, great British statistician. And in the process of working on population genetics, of doing his work in the modern evolutionary synthesis, developed things like the analysis of variance, fundamental to statistics today. Haldane, Oxford-trained mathematician, for some inexplicable reason spent much of his career in Cambridge. He developed mathematical models for the way that natural selection acted, and he found organisms where you could really see evolution in action. It's actually quite difficult to do that. And then Wright, great North American population geneticist, who studied the randomness that comes out of reproduction in a finite population, what we now call genetic drift. Okay. So these guys would all have agreed that Darwin and Mendel together gives us the solution. But what they would have disagreed on is this remaining fundamental question, which is, we know there are a whole bunch of evolutionary forces out there. There's mutation that generates the variability that we need for natural selection to act, so that lies at the heart of everything. There's natural selection, there's random drift, that's what Wright was interested in, this randomness due to reproduction, and things like population subdivision.
Sorry, my computer sounds.
Okay, and what they would not have agreed on is the relative importance of those different forces for standing genetic variation. So what's most important? Is it selection, is it random drift, and so on? So if these guys couldn't solve it, Fisher, Haldane, and Wright are my heroes, right? They're incredibly bright guys. If they couldn't solve it, why do we think we can have any more insight? And the reason is that their work necessarily concentrated on phenotype. It concentrated on observable characteristics. But we have a lot more data at our disposal. Because in the last 30 years or so, we've had DNA sequence data. We've been able to access directly the genotype. And that gives us a wealth of new data, but it's data of a new type. Now, I should come clean. I don't do data analysis. But before anyone else can do data analysis, they require models for what that data should look like, essentially. And so what I want to talk about is those models. And what do they model exactly? Well, what a modern population geneticist does is she takes a sample from the population, and for each individual in that sample, she does some DNA sequencing, so she produces an alphabet of A, C, Gs, and Ts, a sequence of words or a sentence or whatever. And from the variation in that sample, she tries to infer how individuals in the sample are related to one another. So what I'm going to call the genealogical relationships between individuals. What one comes up with is a kind of genealogical tree. We'll come back to that in a moment. And so if that's what she's going to be trying to produce, that's what she's inferring from her data, those genealogical relationships are what we've got to model. And that leads us to so-called coalescent models, which have become one of the hottest topics in probability theory in the last 10 years or so. Okay, so the mathematical challenge that we want to address is we want consistent models for the way that a population evolves forwards in time, and those models must incorporate all of those evolutionary forces that we talked about, and backwards in time models which tell us, if we sample from today's population, what's the distribution of the family trees relating individuals in our sample. Okay? And before I show you some of those models, some terminology, most organisms are either haploid or diploid. Now, a haploid organism is one that carries exactly one copy of each chromosome. Most bacteria are like that. And diploid organisms are organisms like us that carry chromosomes in pairs. There are species of plants that carry tens of copies of chromosomes, but we're not going to go there. In fact, what we're going to do is we're going to concentrate on haploid organisms. So why do I want to do that? It's not essential, but it's essential if you've only got 50 minutes. And the reason is, think about my family tree. If I want to model my family tree, I have to trace my parents, my grandparents, and my great-grandparents. It grows exponentially. But populations are finite. And so at some point, my ancestors were siblings, and I get what I'm going to call coalescences in my tree. So if I look at the genealogical tree, or look at my family tree, I'm going to have something which has branches and coalescences. It's going to be quite a complex object. But for a haploid organism, each individual only has one parent. So as I trace backwards in time, my family trees only get smaller. If I go far enough back, ancestors will be siblings, so I'll get coalescences, but I'll never get any branches. So what I produce will genuinely be a tree. So it's going to be much easier to think about haploid organisms. And there are workarounds for diploids, but I really don't want to go there. Okay, so the first mathematical success, really, and the most important mathematical success to date in modeling genealogical trees has to be Kingman's coalescent, written down by Kingman in 1982. Now, Kingman's coalescent applies to a very idealized biological population. So first of all, it's neutral. Everybody's equally fit. It's haploid. That's what we just said. Everyone has only one parent. It's panmictic. That's just a way of saying everybody experiences the same conditions, right? So there's no structure. Think of everyone living in a big melting pot. And it has a constant size n, and that n is going to be something that's very big. In this kind of biology, we can only model big populations. I need chalk now. Now, before I can tell you what the genealogical trees relating individuals in this population look like, I have to tell you how the population evolves forwards in time. And the workhorse of population genetics goes back to two of my heroes, Wright and Fisher. And in the Wright-Fisher model, the population evolves in discrete generations, and the new generation is determined by multinomial sampling with equal weights. Well, what the hell does that mean? For the non-probabilists, an equivalent way of saying that is that each offspring chooses their parent at random from the population, independently of all other offspring, independently of everybody else. And armed with that description, it's very easy to see what the genealogical trees are going to look like. So suppose, for example, I take a sampler size 2 from this population. Then the only information in the genealogical tree is the time back to the most recent common ancestor of that sample, because remember, the tree is only going to get smaller as I go backwards. So how far do I trace back before those two individuals in my sample had a common ancestor? Well, the chance they had a common parent is just 1 over n, because the first one can choose any one they like, and then the second one's got to choose the same one. So the chance of that is 1 over n. If they didn't, so they've got distinct parents, the chance they had a common grandparent is again 1 over n, right? Because their parents had to, same argument. And so on. And so the number of generations I trace back before I get to the most recent common ancestor is a geometric random variable. So let's write tau for the time to the most recent common ancestor. And it's a geometric random variable with success probability 1 over n. So think of the number of rolls of a die until you get a 6, and then n would be 6. Now, if you've taught first year probability as often as I have, then you have certain facts about elementary random variables stuck in your head. And in particular, that says that the expected number of generations that I have to wait before I see a common ancestor is n. Now, we said n was going to be very large. And so this tells us in particular this is somehow a natural timescale on which to view these genealogical trees. So what I'm going to do is I'm going to measure time in units of 1 over n. In units of n generations. And so the time to the most recent common ancestor then will be 1 over n times a geometric 1 over n. And that is a very beautiful random variable, an exponential random variable with parameter 1, to a very good approximation. So as n tends to infinity, we genuinely have convergence of this to this. So very large n, we're going to suppose that the time to the most recent common ancestor measured in units of n generations is approximately exponential with parameter 1. Okay? So a very nice random variable, easy to work with. That was a sample of size 2. Let's try and be a bit more ambitious. Suppose I take a sample of size k from my population. Is k bigger than or equal to 3? What's the genealogical tree going to look like then? Well, the chance that 3 or more of the individuals in my sample have a common parent is of order 1 over n squared, because the first one can choose any one, the next one's got to choose the same one, that gives me 1 over n, the next one's also got to choose the same one, that's another 1 over n. So the chance that 3 individuals have a common parent in a single generation is 1 over n squared. Okay? I'm measuring time in units of n generations, and I'm letting n go off to infinity. So even in units of n generations, the expected time till I see one of those events would be n squared generations. So that's still n, even when I measure time in units of n generations, so I'm just not going to see it. As n goes to infinity, these events will not be seen on times of order n. So I'm never going to see 3 lineages coming together in a single event. Similarly, the chance that in a single generation 2 distinct pairs of lineages come together into a common parent is of order 1 over n squared. 1 over n for this pair, 1 over n for this pair. Okay? And so again, in units of n generations, I'll never see it. So that means that my genealogical trees are really rather nice. As I trace backwards in time, I follow ancestral lineages, and the only events I'm ever going to see are pairwise mergers, and for each pair, they happen at a rate exponential 1. And I'm never going to see simultaneous mergers, and I'm never going to see what I would call multiple mergers, where 3 or more lineages come together at the same time. So let's draw a picture. I think we've got a picture. Here we are. So if I start with k lineages, the time until I first see an event is the minimum of the k choose 2 exponential 1 random variables corresponding to each of the pairs, and the minimum of k choose 2 exponential 1 random variables is an exponential k choose 2 random variable. Very nice. And at that time, a pair of lineages chosen at random from all the pairs available will coalesce into a single ancestor, just meaning that those ancestors had a common parent. Now I've got k minus 1 lineages left. I have to wait an additional exponential k minus 1 choose 2 time until I see anything else, and so on. So it's a rather simple and elegant description of the genealogical trees. As I say, this is due to Kingman. Okay, but I've done something a bit weird, right? I've measured time in units of population size, and I've let n go to infinity. What's going on forwards in time if I do that with my backwards in time trees? Well, I'm going to suppose the population consists of 2 alleles, 2 types, little a and capital A, and I'm going to write P of t for the proportion of the population that is of type little a at time t. And I'm going to do the same thing. I'm going to measure time in units of population size and let n tend to infinity and see what happens to the proportions of the 2 alleles in the population. Now, that slide needs some explanation. Suppose that
P of t is I over n, meaning exactly I individuals in the tth generation are of type little a. Then in the next generation, sorry, this is the n-th generation because I'm measuring time in units of n generations. So at time t plus 1 over n, meaning one generation later, the absolute number of little a individuals, well, each of them independently is choosing a parent, and the probability that parent is type little a is just I over n. So that means that I've got the total number of little a individuals is binomial with n trials and success probability I over n. And I'm interested in the proportion, so I'm looking at 1 over n times that. Okay. Now, that means in particular that the expected proportion at time t plus 1 over n, well, that's 1 over n times the expected number, and for a binomial, remember the expectation is np, so that's going to be n times I over n. So I just get I over n back again. So there's no expected change in allele frequency over a single generation. And that's what that expectation of delta p equals 0 is meant to be conveying. And that's just neutrality. That's just saying all my genes are equally fit. On the other hand, there will be some variability. So what's the variance of p at time t plus 1 over n? Well, it's going to be 1 over n squared. Remember that variance scales with the square. So I get 1 over n squared times the variance of this binomial. And the variance binomial is n times p times q, which is 1 minus p. So in other words, I'm going to get 1 over n times p of t times 1 minus p of t. Okay. So if I think of this 1 over n, remember I'm going to be letting n go to infinity. If I think of this as an infinitesimal time interval of length delta t, then the variance of the change in allele frequency over that interval of length delta t is delta t times p 1 minus p, where p was the proportion I began with at the beginning. And you can go on with that sort of calculation and check that the third moment, so the expected value of p of t plus 1 over n minus p of t cubed, is of order 1 over n squared, so that's this order delta t squared, and so on. And what that means is that as n tends to infinity, this allele frequency is converging to a solution to this stochastic differential equation. Now don't worry if you don't know about stochastic differential equations, we won't see very many of them. But what this is capturing, you see the expected value of delta p equals 0 is capturing the kind of first order approximation which says allele frequencies are constant. This is capturing the randomness in my population due to the fact it really is finite, even though I'm letting n go to infinity. At any point before infinity, I've got a finite population, and so the allele frequencies will fluctuate. If you like, it's kind of central limit rescaling. And this is what Wright called the genetic drift. Okay, so that genetic drift, forwards in time, corresponds exactly to Kingman's coalescent backwards in time. Okay, so this, to a probabilist anyway, is a very beautiful and simple model. But unfortunately, I can't compare it to data because I've measured time in units of population size and let population size go to infinity. So if I want to compare to data, I want to change back into real generations, time units of generations. So what we do is we just time change, on the one hand, the diffusion equation, and on the other hand, the rate of events in the Kingman coalescent to get back to real intergeneration times, but we retain these sort of continuous approximations. And all that means is that I have a 1 over n inside this square root here, and I have a 1 over n outside here. Oh, but I didn't write 1 over n, did I? I wrote 1 over ne. And the reason for that is nobody in their right mind would believe in the Wright-Fisher model, right? No population, apart from one set up very carefully in a laboratory, is going to follow the Wright-Fisher model. But it turns out that a very wide variety of models can be fitted, or the data that we get can be fitted to a Kingman coalescent, provided that instead of using the real population size here, we put in an effective population size. Okay? Well, okay, but what that effective population size is capturing then are all those evolutionary forces that we want to disentangle. It's capturing the selection, population subdivision, all that kind of thing. The variance in the number of offspring that each individual has. And to give you an illustration as to just how different this is from the true population size, the true population size of humans is something times 10 to the 9. the effective population size of humans that you have to put in here if you want to do your human genome analysis is 10 to the 4. It's 5 orders of magnitude difference. And what we would like to understand is what feeds into those 5 orders of magnitude. What makes that difference? Okay, well, one of the things in particular that Nick and I have been working on for a long time is how spatial structure feeds into the population genetics. And the classical approach to spatial structure, I'm going to run out of time, by the way, is something called the Kimura stepping stone model. And Kimura introduced this model in the 1950s, 1953. One of the things that's truly remarkable is that he introduced a model which was a system of stochastic differential equations within a couple of years of anybody actually working out what a stochastic differential equation was, right? I mean, this is really quite phenomenal. And the idea of the stepping stone model is that the population is subdivided. It's subdivided into islands, geneticists would call them demes, and those demes sit at the vertices of a graph. Within each deme, the population size is supposed to be so big that the Kingman coalescent, or the Wright-Fisher diffusion forwards in time, is a good approximation. But in addition, we now have migration or exchange of individuals between demes. So this is this first term here. It's MJI. And if you like, you should think of that as the discrete Laplacian acting on Z2. Because the way that we choose the graph structure for our demes is to caricature the geography of the population we're interested in. And what happens to that backwards in time is that our dual process, our coalescent, evolves as a system of coalescing random walks. So when different ancestral lineages, suppose there are ni ancestral lineages in the ith of my islands, then 2 of those coalesce at rate ni choose 2, so ni minus 1 over 2, times 1 over the effective population size in that deme. That's just the Kingman coalescence. But now in addition, the lineages follow a random walk between demes. And it's the dual of the random walk they'd follow forwards in time. Okay, and although difficult to analyse mathematically, to get real formulae out of, this coalescent dual is extremely easy to simulate. And so biologists have very much latched onto this model as a good way of modelling spatial structure. But for many biological populations, it's rather unsatisfactory to think of them as subdivided. It's really not natural. And the population that's particularly concerned us over the years, you can barely see it. This photo was once in colour, but I'm not sufficiently technically expert to get a colour into my slides here. This is an organism called Podisma pedestris. You can probably hardly see it, but the wing of this grasshopper is just here. And not being a jumbo jet, it doesn't really equip it to fly terribly well. So the key is in the name. This is a pedestrian grasshopper. It just walks. It can't fly. It's a small flightless grasshopper. You can't see here, but it's brightly coloured. You'd think it would be an evolutionary cul-de-sac because it's of course, small, brightly coloured, can't fly. You'd think birds would pick it out, but apparently it tastes very nasty. Can't say I've tried myself. But what does make it liable to predation is this is where it lives. It lives in the Maritime Alps, and so huge numbers of geneticists enjoy studying this organism. It's easy to catch, and it lives in a beautiful environment. But as you can see, this shouldn't be thought of as an island, a graph-structured population. So how are we going to deal with, I thought I should show you a couple. This one's the girl. How are we going to deal with a population like that? How are we going to deal with populations that are actually evolving in a continuum? And it turns out that Malloco and Wright almost solved this problem way back in the 1940s. So what did they do? Well, they assumed that the population, we're working R2 now. I know the Maritime Alps don't look much like R2, but they're more like R2 than they are like a graph. So they supposed that the population was distributed with a uniform density. And they suppose that individuals reproduce independently of one another. And they leave their offspring in a Gaussian distribution around themselves. So some sort of symmetric distribution. It doesn't really matter what it is. And what they calculated, we're going to need a board again, is the identity in state between genes. Now I would use the same board, except I can see no way to erase it, so I will have to hide behind an overhead projector. Doesn't matter. So what's the identity in state? Well, what we suppose is that as we trace back each ancestral lineage, we see mutations at a constant rate mu. So the chance that as I trace back an ancestral lineage, I have seen no mutation at time, not doing very well here, tau in the past, would be e to the minus mu tau. It's okay, Francis, I'll try to write less.
It's all right, I'll key this forward.
Now, what Maleko and Wright calculate is they say, well, let's suppose that we sample two individuals at separation x from the population. So x is a vector in R2. There's something else I forgot to tell you. When we get a mutation, we suppose it's always to a new type, a type that's never seen before in the population. Okay. This is called the infinitely many alleles model, and it's not as stupid as it sounds. Okay, now as we trace backwards in time along ancestral lineages, at some point in the past, these guys that I sampled at separation x should have had a common ancestor. And let's suppose the time at which they did that was tau. Well then, the chance that they're of the same type is the chance that there has been no mutation along this ancestral lineage and no mutation along this ancestral lineage until time tau in the past. So that's e to the minus twice mu tau, just the square of that. And so the probability that these guys are of the same type is the expectation of e to the minus twice mu tau, right? Where I'm taking the expectation with respect to this random time when they had their most recent common ancestor. And this is called the probability of identity, and it's traditionally denoted f of mu. But you can see that in modern terms, what I'm doing is I'm taking the Laplace transform of the distribution of this random time tau. And if you want to make a quick career, you go out and you read the population genetics literature, which almost exclusively deals with this quantity, and you translate it all into coalescent theory by taking the Laplace transform. So, no, there are two completely separate literatures that have built up. But these guys can be excused because no one thought in terms of coalescence. And what they did was they wrote down this equation for the probability of identity of two genes sampled x apart. And by taking the Fourier transform, they solved it-ish. It doesn't actually have a solution. If you try and solve this in two spatial dimensions, you discover yourself with a Bessel function of order 0, which blows up at the origin. But we're looking at a probability here, so even my weaker undergraduates can usually be persuaded it should lie somewhere between 0 and 1. So if this blows up, we're in trouble. On the other hand, if one assumes that over some sort of local scale, the probability of identity is constant, then one can come up with a sensible solution. But there are other mathematical problems. So what are the other mathematical problems? And here's where the title pain in the torus comes from. So remember that what Maleko and Wright assumed was that the population was uniformly distributed in space, and individuals reproduced independently of one another and threw their offspring around themselves according to a Gaussian distribution. But what Felsenstein observed in 1975 was that independent reproduction necessarily in two spatial dimensions would lead to clumping of the population. So either the population dies out, which isn't terribly biologically interesting, or, if you're seeing an individual in your sample at least, or it clumps. It produces clumps which are arbitrarily dense and arbitrarily big. So unless you're modelling locusts, you don't think it's a good model. But in particular, it's not consistent with the assumption that we've got a uniform spatial distribution. And so Felsenstein thought, well, what can we do about this? So he started working on a torus, but that didn't help. And then he started conditioning on the total population size on the torus, but that doesn't really overcome the problem of clumping. We still don't have a uniform distribution. And so he wrote a very, very famous paper called The Pain in the Torus, throwing down a challenge, if you like, saying, I really can't solve this. If the only way he could see to control the clumping was to introduce some sort of local regulation to population size, but that means we have to consider correlated reproduction, and that makes the whole subject a mathematical nightmare. Okay, well, so Maleko and Wright's model didn't work, but the stepping stone model was this great model, and that seemed to work very well for subdivided populations. So can we modify the stepping stone model? Well, oh, thank you, Francis. Let me remind you what the stepping stone model looked like. Well, let's not write it like that. Let's suppose that we're working on the Z2 lattice, and then my stepping stone model becomes something like this. There may be some factors of a half that I'm missing somewhere along the line. That's the WI. Okay. So this was a system of stochastic differential equations. Now, a classical stochastic differential equation should really be thought of as an ordinary differential equation. Right? Forget this bit for a moment. you've just got a single driving noise. It's an ordinary differential equation. If, as an applied mathematician, you're trying to model something in a continuum, rather than considering a system of ordinary differential equations, you might think you could use a partial differential equation. So the natural thing to try, and it's actually what Barton did try in the first equation he came to me with, is to replace the system of stochastic ordinary differential equations by a stochastic partial differential equation. So I put a genuine Laplacian in here, and I replace these independent Brownian motions by something called white noise. The problem is that equation doesn't have a solution. If it did have a solution, it would be a distribution, and then you can't make sense of this. Actually, I think Nick still doesn't believe it doesn't have a solution. He told me it was my job to make it have a solution. And for a while I thought I'd convinced him that I can't make equations have solutions, but I think actually he's just given up asking. I don't think he really believes me. But anyway, it goes wrong. And also, the obvious backwards in time model fails. So replacing the stepping stone model with the obvious forwards in time model failed. But the stepping stone model had these genealogical trees which were coalescing random walks. Maybe we could replace coalescing random walks by coalescing Brownian motions. Brownian motion is a natural analogue of random walk. And the problem is that in 2 dimensions, Brownian motions don't meet, and so they never coalesce. So we lose what corresponds to this part of the equation, which is all the interesting stuff about finite population size and genetic drift. So modifying the stepping stone model doesn't seem to work either. Something lots of people tried was to say, well, okay, Brownian motions don't meet, but individuals have real size, so you shouldn't be asking Brownian motions to come to exactly the same point. Maybe if they just got close by, we could have them coalesce. So they proposed a model where you trace back ancestral lineages until they get to within some distance of each other, and then they coalesce maybe to the midpoint of, well, some point centered on their midpoint. But there's a difficulty with that model too. Well, there are lots of difficulties, but one fundamental difficulty is that suppose that I do this with a sample of size 3. So there's my genealogical tree for a sample of size 3. These guys came together and they coalesced, and then their ancestors came together and they coalesced. Well, the tree that I get for this sample of size 3, I could say, well, let's throw away some information and just see what it tells me about the genealogical tree of this sample of size 2. And the genealogical tree of this sample of size 2, these guys follow Brownian motions, but at this point, this lineage jumps. And then we move on, and then they coalesce in the usual way. And the difficulty is that, therefore, this induced tree is not the tree that I'd have got if I'd modelled the genealogical tree of these 2 guys just on their own. And that means I'm losing what's called sampling consistency. And if we're going to interpret these things as genealogies of samples, we would really like sampling consistency. So we have to throw that away too. Okay, but on the other hand, Malako and Kimura are not so far apart. So this is where I wish the colours didn't show up. This is from a very old paper, and I can't remember why those are in red. However, what this corresponds to is probability of identity in the Kimura stepping stone model for 3 different population sizes. It's in 2 dimensions, so the red ones are somehow off diagonal. We're measuring distance in Euclidean distance. So that's neighbours, next neighbours along an axis. And what we fitted here, the curves, are the Wright-Malako approximation to the probability of identity. And you can see that apart from the fact that they blow up at 0, they give an extremely good fit. So Wright-Malako somehow is the right continuous approximation to a Kimura stepping stone model. So there's something good going on there, but what? Okay, so that was mathematical problems with Wright-Malako and trying to rescale Kimura. What about biological problems? We've already said genetic diversity is much, much lower than you'd expect from census numbers. That was one of the first things we said. The other thing is that allele frequencies actually don't follow that pattern that we saw on the last slide of decaying exponentially. They're in fact correlated over very long distances. And a possible explanation for both of these things is that the demographic history of many species is actually dominated by large-scale extinction recolonization events. So my favourite example is that 20,000 years ago, or 2 months ago, depending on your perspective, most of northern Europe was covered in ice. Right? The last ice age was only 20,000 years ago. And given that we're measuring time, oh, you deleted it, Francis. Given we're measuring time in units of n generations, that's the twinkling of an eye in evolutionary timescales. So over evolutionary timescales, we can expect species or organisms whose history we're following to have experienced large-scale extinction recolonisation events, and they're simply not incorporated in the classical models. And something else that I would like to say is that in a spatial continuum, neighbourhood size, which basically says how many potential parents are there for an individual to choose in the region around them, well, it could be rather small, right? And then pairwise coalescences may not dominate. If I look at the dandelions in my backyard, and there are a whole bunch of them there, I can assure you, but I also know they're all descended from a single parent, and my son got the dandelion clock and blew the seeds everywhere. I know that pairwise coalescences are not dominating in this spatial continuum where neighbourhood size is small. Okay, so can we find a model that overcomes these mathematical and biological problems and also allows us to incorporate these large-scale events? And the answer is we can find a whole family of them, but I'm just going to explain one of them to you. I want you to think of this as a framework for modelling, and I'm going to explain one simple example. So what we're going to do, we're going to try and be as much like Wright-Malakoff as we can. So we're going to start our population from a uniform intensity in the plane. So mathematically, I have a Poisson point process with just a constant intensity. And then I'm going to throw down events. Now these could correspond to regular reproduction events, or they could correspond to big extinction recolonisation events. And what does this mean? This means I'm throwing them down somehow uniformly in space and uniformly in time, and this measure mu of dr will tell me how big the event is. When one of these events falls, it throws down a ball of centre x and radius r. If that ball's empty, if no one's living there, I don't do anything. Nothing happened to my population because there's nobody there. Otherwise, I choose a parent just uniformly at random from those available. I could choose a bunch of possible parents, but I'm just going to choose one for this illustration. I pick a probability according to some measure which may depend on the size of the event. So just think of a half if you like. And each individual in the region dies with probability u. Okay? And then I replenish the population with offspring, and they're born according to, just within the region, according to an intensity which will just be enough to replace the ones I died. It's not quite how it works, but it's pretty close to how it works. So here's a picture. There's my population, uniformly distributed in the plane. I throw down an event, a ball of radius r centered on x. I choose a parent, that's the one now in magenta. Now I've chosen a u, and I flip it independently for each of these individuals, including the parent, and the ones with crosses through them are unfortunate and die. And then I replace them by throwing down independently some magenta offspring. Okay? Now it turns out that if the lambda, the sort of intensity with which I threw down the population in the first place, is sufficiently large, then the population survives with positive probability. That's a joint result with Nathaniel Berestiki, who told me he couldn't be bothered to get up in time to come this morning, and an ex-postdoc of mine called Martin Hitzenthaler. And so we've got some sort of, moreover, simulations show that this thing is kind of uniformly distributed in the plane. It's much more like Wright-Malakoff than their model. But the possibility of empty regions means calculating anything gets very cumbersome. There are two ways around this. One is, I've shown you a model where we replace individuals, well, there are more than two ways, but here's one. I've shown you a model where we replace individuals in a disk. We think of reproduction events as being disks. If instead we decided to have some sort of Gaussian density, then we'd never have the empty region problem, but we could have parents coming from a hell of a long way away. So Nick favours this solution. The solution I favour is to just let lambda tend to infinity. Now that sounds like it's getting away from the finite neighbourhood size, but in fact it's not. Because of the way the model is set up, it's still going to be the case there's a significant proportion of my ancestral lineages can coalesce in a single into a single parent in a single reproduction event. And this actually is a signature of finite neighbourhood size. So I don't want to say more about that. The model that we come up with is something one might call a spatial lambda-Fleming-Vio process, but I certainly don't want to explain that. But the point is that forwards in time we do have a coherent description for this thing. It's a measure-valued process that evolves forwards in time. And backwards in time we can really talk about the genealogy, and it's consistent. And what happens is lineages follow coalescing Lévy processes. Well, the processes that instead of having Brownian motions, we have lineages that jump. But we could see already from this picture that as soon as you had a possibility of individuals coalescing into a single parent when they were at neighbouring points instead of sitting on top of each other, they were going to have to jump. And now I jump whenever I'm hit by a reproduction event. So my ancestral lineages move around in jumps, and they're not necessarily independent, because if a single reproduction event can hit two lineages, they're dependent. And they coalesce. There's some probability that they can coalesce, and this coalescence actually allows multiple mergers, so mergers of 3 or more lineages at a time. But what's important is this consistency. We've got consistent forwards and backwards in time models. So let's show you some pictures, and that'll be it. So, and tell you why it all works. So somehow we've solved the mathematical problems that we raised. By taking the size of these events to be different, I can have large-scale extinction recolonization events and small-scale reproduction events in the same model. The sort of patterns of allele frequency we get, these are pictures produced by Jerome Kelleher, who's a postdoc of ours in Edinburgh. We've taken 2 alleles, which always were labelled black and white. This is the starting point. This grey is exactly half black and half white, and we started from that uniformly across the plane, so the intensity is somehow uniform. And then he's thrown down 40 reproduction events, and I can't remember what parameter he took for U. But you can see that if we have this disk replacement model, we get very sharp boundaries between different allelic types. This thing on the right is not myopia on your part, it's what happens if you do a Gaussian replacement. Okay. So how does this perform biologically? Well, one of the things we said was genetic diversity was much lower than expected from census numbers. In joint work with Nick and a graduate student, Almudine Weber, we've been able to show how these large-scale extinction recolonization events feed into the effective population size in this population. So we can obtain a Kingman coalescent limit and see how these big extinction recolonizations really drive the genetic drift in the direction suggested, in the direction it should be driven. I mean, the genetic diversity really should be much lower than expected if you have these large-scale events, and we can say quantitatively how. The other thing we said was allele frequencies are actually correlated over long distances. Well, here's another picture that Jerome produced. So what's this? If we look at Wright-Mallico and look at the probability of identity, we said we had an exponential decay of allele frequency, of correlation in alleles, so an exponential decay of the probability of identity over time. If we look at, let's say, the disk model with just one size of event, small events I'm going to call them, so rather small events, then this straight line is the logarithm of the probability of identity. So it's exactly what Wright-Mallico predicts. If we just have large events, this is what we'd have. That's exactly what Wright-Mallico would predict for a model where you just had large events with a different slope. If we allow a mixture of events, so lots of the time individuals are just doing ordinary reproduction, and then once in a while an ice age hits them or a forest fire hits them if they're plants, then we get this, which is much more characteristic of what we see in data. Okay? So we somehow also overcome the biological problems. Okay, now I'm not going to show you that one because it almost certainly won't show up. I'll show you a movie. So for me, oh God. Does anyone know how to tell these stupid computers how to alphabetize? There we go. So for me, what's exciting about this framework for modeling is that we have a replacement for stochastic partial differential equations. The theory of SPDE is inadequate in 2 dimensions if you're interested in biological models especially. And what we now have is a consistent way of putting a little bit of noise back in. So we've got something that can replace this term. Now, one of the things we really, really would like to understand is the way that an organism that has, or an allele, a genetic type that has a selective advantage spreads in a 2-dimensional population or in a spatial population. We understand in a panmictic population, when we understand in a 1-dimensional population, but actually there aren't very many 1-dimensional populations. What we'd really like to be able to do is do it in 2 dimensions. Now, if we have no noise, if we assume the population is somehow infinitely dense everywhere, Fisher did it. He wrote down the Fisher KPP equation, and the Fisher wave gives us a way of modelling things. But we know that genetic drift, that the finiteness of the local population density matters. And so what we would like to investigate is how putting a little bit of genetic drift back in will change the Fisher wave. Now, we haven't done the math yet, and indeed I'm writing a grant application so someone else can do it, but we did do some simulations. So this is one of Jerome's simulations as to what the Fisher wave will do in 2 dimensions with this kind of replacement. So this is the disk replacement model. And you can see it does spread out broadly in a circle, as you'd expect from the Fisher KPP equation, but there's quite a lot of noise in there up for quite a long time. And we're really interested in understanding what's going on in this region here, this mucky region at the edge. Okay, and that's kind of where that one stops. It's on a torus, so it's now interfering with itself at the edges. But it takes a long time, right? And then let's show you what happens if we do Gaussian replacement. This one is not for the faint-hearted. It actually makes me feel a bit queasy, so I'll probably not look at it. So this is what happens if you do Gaussian replacement. So our next task is really to try and understand these pictures mathematically. Well, but not that one. Okay, and I'm only 2 minutes over time, right?
Yeah, that's great.
Thank you very much.
That was it. So, anybody have a question or comment? No, everybody too queasy looking at the picture.
Yeah, I have a small question about the selection.
Mm-hmm.
When the parents generate offspring, in
Yeah.
some cases the selection is done like only the offspring can go to the next generation and the parents are dying. In some other cases, they are compared. There is a competition between the offspring and the parent. Which one
Yeah.
is better? That go to the generation. In your case,
Well, we just presented a very simplified version. I mean, of course, you
which
could,
one is better will go to the next generation, whether it is the parent or the offspring?
No, in our case, well, it
Just the
depends.
offspring.
The problem, one of the problems of this model is there are lots and lots of different ways of introducing selection, and at the moment we are the fitter parents have a better chance of producing offspring. Is the way we're doing it. But there are a multitude of different ways. You can do so-called viability selection, fecundity selection. You can even do balancing selection, which won't look like this. There are too many different ways to list, and that's just it's a modelling question. At the moment, the simplest one mathematically appears to be when the probability of choosing a particular parent depends on their genetic type. So the fitter individual has a better chance of being a parent. They don't produce more offspring, but they have a better chance of being a parent. So it has the same effect as producing more offspring.
Any other questions? Can I just ask, is there any hope of bringing in 2 parents to this?
Oh, absolutely. Yeah, we've done that. It's just
Okay.
much like, yes. I mean, I'd need 3 hours.
Yeah. Okay.
Yeah, we've just written the paper on it.
Anything else? If not, let's thank Alison again. And I think we're starting Kenneth at 10 or just after 10. Let's see. Okay, thanks very much.